Welcome to Carnegie Mellon Online. For more multimedia from Carnegie Mellon University, visit www.cmu.edu/multimedia.
Thank you, Rick, for your kind comments. As you can see, they were so kind that I started to cough. It was all, but it is my great pleasure to dedicate this talk to Rick McCullough because of his contributions. He's a person who I've so much respected for so many years because of his pioneering work in developing new types of conducting polymers for their application in devices, for his starting a company that I think has over 50 people in it now, and for his leadership at Carnegie Mellon University. It's my pleasure to dedicate this lecture to my friend Rick McCullough. I just going through campus, there's just so many beautiful memories of people and events and joys that I've had at Carnegie Mellon as an undergraduate student. And still, when I think of academic scholarship and when I think of having a good time, I think of bagpipes. And I think somehow Carnegie Mellon is the thing that connects the bagpipes to everything else. But it's such a great pleasure to be here. And I'm very good at looking at the audience and seeing when people go to sleep. I have many more slides than I could ever show. And so I will look at you. And if you have a question you'd like to ask me during the talk, or if you don't believe something, want me to expand on something, please interject anytime you want to. And the purpose, of course, is for us all to have fun at these types of things. Now, the level of the talk is sort of, I have on the slides a lot more detail than non-experts would be interested in, and not enough detail that many experts would like, but I could, if you have questions for the experts, I'd be happy to elaborate. And what I'll be talking about is basically nanotechnology for fun and profit. I'll be talking about lots of different things, everywhere from artificial muscles to indicators for vaccines to solar cells to organic light emitting displays, various ways of harvesting energy. If I can figure out where I can get the screen on. Here we go. The work that I'll be described is done at our Nanotech Institute. I worked for 31 years in industry, so I both love doing fundamental work, but also equally love seeing fundamental breakthroughs that we make being turned into products. I like applications, but at the same time, I like to be able to predict the mechanical properties of the skin of a neutron star, although that might not be such a practical item. Now, our institute was, let's see, I hope I have the right collection of, yeah, I do have the right collection of slides. Again, what is the nanoscale? The nanoscale is defined as physics and chemistry and other processes that are biological processes that are occurring on the scale of 1 to 100 nanometers. What is a nanometer? It's 1/1000th of a meter. Now that's 1/1000th of anything is very hard to wrap your mind around. But if the ratio of 1 to 1,000,000,000 is the ratio of the diameter of a marble to the diameter of the Earth. That's still one I have a hard time wrapping my mind around, but at least it gives you a chance. Now, though I'm not really qualified to make this type of comparison, a nanometer is 100,000 smaller than the diameter of a human hair. The point is that when you go to the nanoscale, you see remarkable new physics and chemistry and other types of processes. Nature's recognized that these new processes occur on the nanoscale, and she heavily utilizes them for her types of catalysis, for example. Now, should we be afraid of nanotechnology? I believe that there's anyone who writes that a nanomaterial has a biological effect, he or she gets lots of press. Of course, many papers that are written about no significant biological activity is ignored. So, the bias in terms of what the public sees is of that type. And for any chemical, there's our health issues, that have to be determined, what the risks are, if there are risks, and how serious the risks are for particular applications. And I think this is the same case for nanotechnology. I'll be talking a lot about carbon nanotubes. Now, carbon nanotubes, many people say they kill cells. I have movie clips that show in our carbon nanotube sheets and yarns neurons, very sensitive type of cell types, propagating in a normal way, having normal cell lifetimes and growing much faster than on artificial substrates. And they seem to love carbon nanotubes. But again, the whole story is not out for any one of many important types of nanomaterials. And even today, our most commonly used chemicals, people find biological effects long after they've been used for many decades. Again, we focus a lot on developing intellectual property in our institute. We like to make inventions, and we like to see those inventions utilized. And one way to ensure that these inventions are eventually utilized is to take them seriously by patenting them, and patenting them very broadly, internationally. For example, I usually write my own patents. This one is a key patent, which is really about PCT filing says it's 57 separate inventions, 425 pages, lots of examples, lots of figures, and lots of claims. That particular patent was focused on the synthesis and application of carbon nanotube sheets and yarns. So I'll tell you a little bit about that. Carbon nanotubes, individual carbon nanotubes are well known to have spectacular properties. The individual nanotubes can have a strength that's 10 times higher than for commercially available yarns or fibers. They can have higher thermal conductivity than diamond. They can carry 1,000 times higher current than copper, even though they have far lower electrical conductivity than copper. They have low density, high thermal and radiation stability. Well, what's the problem? Well, these individual carbon nanotubes are like minute bits of string. And how do you assemble untold trillions of these minute bits of string so that the bulk article, a sheet or a yarn, has properties that are exciting? Well, our first route for doing this assembly resulted in the world's toughest material. When you say a material is strong, you mean that a large amount of force per cross-sectional area must be applied before it breaks. And when you say a material is tough, it means that a large amount of work must be done before you break the material. Materials that are very tough are of great interest, for example, for anti-ballistic vests. Using a spider silk is a very tough material. In fact, prior to our work, it was known as the toughest material. It has a toughness of about 150 joules per gram, joule being a unit of energy, gram, of course, weight. We've made carbon nanotube yarns that have a toughness of about 600 joules per gram, which is of course, spider silk is about 5 times tougher than steel wire, and the carbon nanotube yarns are about 5 times tougher than spider silk. And how do we make these yarns? We make them by solution spinning. We take a dispersion of carbon nanotubes in a liquid and inject them into what's called a coagulation bath. This is a mixture of polyvinyl alcohol and water. The carbon nanotubes come out of solution at the same time as they are bound together using this polymer, polyvinyl alcohol. We are no longer focusing exclusively on this type of solution-based spinning. Why not? Well, the problem is, if you really want to harvest the extreme mechanical properties, thermal properties, electrical properties of carbon nanotubes, you really want carbon nanotubes which are very, very long, because every time you get to the end of a carbon nanotube, the electron or the phonon has to get to the next carbon nanotube. And that process, the unlikelihood of that process in some cases degrades the overall properties of a yarn and sheet. And you can't process from solution or melt very long carbon nanotubes. It's basically solution or melt processing is limited to short nanotubes. So what we did is develop a solid state fabrication method for carbon nanotube yarns, which starts with a forest of carbon nanotubes. Now, what's a forest of carbon nanotubes? Well, a forest of carbon nanotubes, I talk for 2 hours, right? I just realized that I'm talking much slower than a forest of nanotubes is, think of a bamboo forest. It's each of the carbon nanotubes are like trees in a forest, a bamboo forest. But these trees are so narrow compared to their length. It's like having a bamboo tree that's 1/2 inch in diameter and 1/2 mile tall. Now, Chinese researchers had discovered that you could pull a yarn from the side of a nanotube forest. But the yarn strength was extremely low, not usable. We discovered if we just deployed an ancient technology of twist-based spinning, basically deployed this twist-based spinning on the nanoscale, that we can increase mechanical properties by a factor of about 1,000. And as a result, we're able to make singles yarn, 2-ply yarn, 4-ply, knitted yarn, knotted yarn. We can make a 20-ply yarn with the diameter of a human hair. What is special about these yarns? Well, if you take any fiber from the Kevlar, the Spectra fiber that are used for anti-ballistic vests, to a wet noodle or a strand of DNA, and you knot it, it will break at the knot. These carbon nanotube yarns do not break at knots. Now, why is this the case? This is an inherent feature which arises because of the nanoscale of our fibers within our yarns. Now, if you look at this knotted yarn, you can see the radius of this knotted yarn is about 5 microns. That 5 microns radius, even though it's very small, about 1/20th the diameter of a human hair, is giant compared to the diameter of the individual carbon nanotubes that are in this yarn, which are only about 20 nanometers. So the individual nanofiber in the yarn doesn't even know it's knotted. It's so deviating such a small degree from a straight line compared to its diameter. Similarly, the loop strength of our carbon nanotube yarn, which is the strength measured when you have 2 fibers looped together, is a little degraded from that of the parent yarn. Our twist-based yarns are tough. They have a toughness comparable to that of the Kevlar that's used for anti-ballistic vests. They're far from as tough as our super tough yarns that I first mentioned about. However, if you knot Kevlar, it loses its toughness. If you expose Kevlar to ultraviolet light, it loses toughness. If you take it to too high a temperature, too low a temperature, it loses toughness. So the mechanical properties of our yarns are very interesting and still far from where we will eventually be able to take them. The toughness of carbon fibers is about 12 joules per gram. If you take a tow of carbon fibers and try to break it, you never could break them. You tie a knot in it, it just breaks so easily. Again, showing its vulnerability to knotting. We can take these carbon nanotube yarns and make intense lights from them just by putting a nanotube yarn in the middle of a cylinder that has fluorescent material on the surface of it and a current collector. You get two different types of voltage amplification effects. One is due to the fact that you have all the field lines are converging on this filament, but also the filament has little hairs sticking out of it. And these hairs give you a second type of field amplification effect, which allows you to operate the lamps at low voltages. Here we showed Anvar, who did most of this work, Anvar Zakidov, Rick and my mutual friend, our buddy, used the carbon nanotubes as cold electron emission sources in order to make the static display. We can take these carbon nanotube yarns and make them into supercapacitors that we can weave into textiles using the Martha Stewart method. I have high school students who won awards at a major Korean, Japanese, Korean, US technological meeting because of their using these carbon nanotubes in textiles for providing sensory input for possible application in prosthetic limbs, where the idea is basically carbon nanotubes in the textile. This is not an example of the sense of the artificial skin, but where you have carbon nanotubes, yarns that are in opposite directions, perpendicular directions, would act as little switches, determining the degree of local pressure. This is the first woven carbon nanotube textile. It was made by one of our high school students in not this last August, but a year August. She wove it on a hand loom. Every time she added a line of carbon nanotube yarn, she only increased the width of the fabric by the diameter of a human hair. As a consequence, and so the yarn was very small in dimension, but this was a concept demonstration. It showed you that you can make carbon nanotube textiles. She made it by hand. She made that much over 3 days, but on a machine, it's clearly a scalable process. As a consequence of this high school student's work, Diane Chen, her picture was in Science magazine. My picture's never been in Science magazine. In honor of George Jeffrey at the University of Pittsburgh, I call our nano explorers the George A. Jeffreys Nano Explorers. When I was entering 10th grade in high school, I really wanted to be a scientist, so I put my suit on, went over to the university, but a giant rainstorm came down. So I arrived soaking wet, met Professor Jeffrey, and he gave me a job working at the university. And so in honor of him, what he did for me and what he's done for other people, we call our high school students the George A. Jeffreys High School Nano Explorers. Our Nano Explorers have won many, many prizes. They continuously, last week, for the Siemens competition, they are finalists. Instead of drawing out carbon nanotube yarns from a forest, we discovered we can draw out a sheet. I have many funny stories about these sheets, but don't have time to tell them. It's a very, we pull the carbon nanotubes out from the forest and you get a transparent sheet. This sheet is an aerogel. I'll show you movies at the end of my talk illustrating this strange type of aerogel. Guinness Book of Records lists the lowest density aerogel as having a density of about, it's made by NASA, it's a silicon based silicon dioxide, and they claim it has a density of about 0.003 grams per centimeter cube. The density of these carbon sheets is about 0.0015 gram per centimeter cube, half as much. But these carbon nanotube sheets have strength, remarkable strength. The aerogels, of course, are not very strong. But on a gravimetric basis, these sheets that we pull out of carbon out of the forest, which is down here, have a strength which is higher than the Kapton and the Mylar, which is used for ultralight air vehicles, and for stronger than the strongest steel plate. On a per weight basis, that's why if this sheet is densified by a process in which we expose the sheets to a liquid, allow the liquid to evaporate, the thickness of the sheet is only about 30 nanometers. And again, which is of order 3 orders of magnitude lower than the diameter of a human hair. It's probably why I have so little hair. I talk about it so much. Here's carbon nanotube sheets plied. Here's the sheets being pulled out of a forest. I have movies I can show you later on. Here is a picture taken by National Geographic magazine. The National Geographic photographer wanted the June bug to be able to tear up our carbon nanotube sheet. And we, of course, wanted to ply our sheet. In other words, put the strong direction, which is this direction, one sheet matched with the orthogonal with another sheet. But you can see here this June beetle bug is being supported by this ultra-thin nanotube sheet. The force that the nanotubes underneath that each of these legs is supporting is about 1,000,000 times higher than the weight of the underlying carbon nanotubes.
When you make the forest, is it a forest of bundles of individual?
I'll tell you about that later on. There's something called intermittent bundling, and intermittent bundling is key for this process to occur. And you can see there's interesting scale-dependent. Go ahead.
No, keep going. Well, I was just wondering, how do you grab the nanotubes to pull them out of the forest?
With small hands. It's very funny. You notice I have a movie of this, but that's a piece of Post-it note. To pull the sheet, we take a Post-it note. And there's adhesive on the Post-it note, and the carbon nanotubes become attached to that, and you draw. Relevant to the issue of bundling, which is a very important question, and also order. Notice that you can see very clear high degree of alignment here. But alignment, degree of alignment is scale dependent on very high magnification scales. You see a type of self-woven structure where individual nanotube bundles go along and they fork and they combine with forks from other nanotubes in order to make a self-woven structure. We can use these carbon nanotube sheets, even though they're so thin, we can move them around easily, assemble them. We've published a paper on using these nanotube sheets because they are transparent to ions for ion stripping for accelerators. We can make these carbon nanotube sheets so that they are elastomeric. It's a very simple trick. What we do is we take a silicone rubber, stretch it, slap on the carbon nanotube sheet. Now allow the silicone rubber sheet to go back to its original dimension. Now we can reversibly stretch by 100% the carbon nanotube sheet without causing its change in electrical conductivity. You're only allowed one question for summer. He talked to me all last night. I'm going to start charging a consulting fee.
Okay.
I'm just joking.
I'll pay it. What happens to the electrical properties when you stretch it?
Yeah, that's what I said. The conductivity doesn't change. And this is very important. People want high-stroke artificial muscles. And artificial muscles is an area in which I do a lot of work. The problem is people can get an artificial muscle stroke of 300%. But what electrode material can deform 300% or even 100% or even 30% without changing its electrical conductivity? So what people do, if they use an artificial muscle material such as silicon rubber, they put greases that are loaded with conducting particles as on top of the sheets as electrodes. Now the thickness of the grease has to be a certain amount or you can't use an electrode. So unless you use thick silicon rubber, your whole actuator stack, your artificial muscle stack will be all grease. So I saw that person leave. Actually, I did. Pardon me?
In a private class.
No, I'm just kidding. I have a bad sense of my humor. My wife says, never try to be humorous, right? No one will ever laugh at your jokes. At the end of the program, there's a ABC news show on artificial muscles, in which there's a joke, and try to laugh at it. Very few audiences ever do. Again, I have to move on very quickly. We very recently we joined with a company called Tercia, discovered that carbon nanotube sheets provide very exciting antenna materials for magnetic resonance imaging. Apparently the reason that they do is that the sensitivity of antenna for magnetic resonance image goes as the square root of the inductance divided by the resistance. And the inductance factor seems to be what is providing a major advantage. Right here you see a mouse's brain. You see resolution of 250 micron diameter blood vessels. We still are far from, and here we show the carbon nanotube sheets being wrapped up into an antenna. The antenna that we made had much less nanotubes than we believe is optimal, but being able to obtain this high degree of resolution at this point is very, very exciting. We can take these carbon nanotube sheets and use them as incandescent antennas. Now you say, well, what's exciting about that? Edison, over 100 years ago, used carbon for filaments for light bulbs. But these are very unusual light bulbs. First of all, the planar, this is the nanotube sheet, it's off and on. The individual nanotubes act like little antennas. So the light that's emitted from these carbon nanotube incandescent sheets is highly polarized. Also, the amount of mass per sheet area is only about 3 micrograms. So there's very little thermal inertia. You can turn the sheet on and off very fast. So if you went to, for example, instead of using a shutter on an optical device that needs very fast switching and opto-polarized light, this is a cheap solution. ONVAR has done an enormous amount of work on using carbon nanotubes for solar energy harvesting and also for organic light emitting displays. Here we're using not only the fact that the carbon nanotube sheets are transparent, not only the fact that they're mechanically robust, but also the fact that we can tune the work function of these carbon nanotube sheets, and also that these sheets are highly porous. That means that organic materials can infiltrate into the electrode and provide very high area for charge injection, either holes or electrons. Again, we've done work with Scottish Rite Hospital and University of Texas Southwestern colleagues there, and find that these cells just seem to love to proliferate on the carbon nanotube sheets. So, in fact, we're starting to work with Cochlear Institute in Australia from the viewpoint of using carbon nanotube yarns for making connections from the hard electronic world to the electronic world or ionic world of neurons in the body. One of the major problems with cochlear ear is the degradation of the connection like between leads and neurons. Texas has been, is, and I say will always be the energy state. Please don't forget to write down your Texas sayings. Okay. I see when I'm in Texas, I always ask an audience to write down Texas sayings because I love Texas so much I collect sayings from there. Like, money can buy you a fine dog, but only love can make the tail wag. Or one from Ross Perot, who's interested in nanotechnologies. So I had an opportunity to talk to him about it. He says, you find a snake, kill it. Don't form a committee on snakes. Remember, he was the person who sent in a private army to get his people from IDS out of Iran. So that's a very appropriate statement. And now you understand that why my lectures are also very difficult to time. Being in the energy state in the historical past meant we had oil in the ground, and we had technology for getting the oil in the ground up to the surface. What it means to be an energy state in the future is something very different. And we are working on many parts of this future. And for example, the beginning of the week, I was up at General Electric in Schenectady, and we were working in energy storage with General Electric. We're working with other companies in another type of energy storage aspect. We work on waste energy harvesting, thermoelectrochemical energy cells that take waste temperature differences and electrochemically, not by using a thermoelectric, convert this these temperature differences into useful electrical energy. Again, solar energy, mechanical to electrical energy. I won't go through all this, but one of the areas that we especially are interested in as far as energy processes, energy conversion in artificial muscles. Now, our carbon nanotubes, surprisingly, we discovered a long time ago, can act as artificial muscles in an electrochemical cell, and this is work done with John Madden. We can generate about 100 times the force of natural muscle. In other words, comparing the same cross-section of natural muscle and carbon nanotubes. We can obtain twice the strain rate for actuation, in other words, displacement as natural muscle. And the effects here, there are beautiful physics associated with these artificial muscles in terms of the quantum mechanical effects and how that depends upon the chirality of the nanotubes. But in reality, the physics that's relevant for these artificial muscle actuation is very trivial. You're putting charge on a cylinder, that charge wants to get away from each other, so it causes your nanotube to expand. The beautiful physics, the quantum mechanical effects are at low degrees of charge injection, which are less relevant. I'll just show you some of the reasons, of course, you want improved artificial muscles. If you look at, we have a lot of people who have lost their arms and legs in the wars, Iraq and other places, and accidents. And if you look at the prosthetic limbs that are available now, this is a modern prosthetic limb. Mechanically, they look as primitive as ones you can find on the web from the Civil War. They have degrees of sophistication in other ways. This particular artificial limb is controlled, it takes a signal from nerves that are moved to his chest area, and they take the signal from them. I met some beautiful women in Korea last year, and They look very beautiful from a distance. But when I got closer to them, they seemed unnatural. Because one of them seems to still be objecting to them, and I didn't do anything. But inside, the humanoid robots inside, you can see they're very primitive mechanical affairs. And why was her smile unnatural? Because it takes about 30 muscles to express sadness or happiness, and she just didn't have enough muscles in that region. And so our carbon nanotube yarns can be a diameter of a human hair. They can, depending upon compositions that we use, they can have giant strokes that are much larger, and that's fractional displacement is much larger than natural muscle. For the carbon nanotubes, the strokes are very small, much smaller than for natural muscle. But I'll show you movies, and I better be careful of timing, because the timing is I'm close to the end of it, I'm afraid. So I'll have to skip through a lot. DARPA came to me, John Main from DARPA, and he asked me to work on a particular problem that's indicated here. This is Honda's Asimo robot. It can play soccer. It can get up if it falls down, climb stairs. However, intense physical activity, it can only power itself for 30 minutes before the battery has to be recharged. And recharging the battery takes about 4 hours. So the point is, the amount of energy that you can store in a artificial muscle, in a electrically in battery, is very small compared to the amount of energy that you can store in a fuel such as methanol or such as hydrogen. So what John Main asked me to do, because he knew we worked and discovered a number of new types of artificial muscles, he said he wanted our team to develop chemically powered artificial muscles for the robotic soldier that could fight ahead of the American soldier, take the bullets for the American soldier, and then drink a shot of alcohol in order to fight on. Like what?
Like the American soldier.
Or the Irish. Again, you know, we have two ways of making these fuel-powered artificial muscles. That first of all, the first 4 months of a DARPA program, you can't sleep in the morning because you haven't gotten any results, and they really depend upon results. And but after 4 months, we had a breakthrough, and so we had developed two different types of fuel-powered artificial muscle. In one type of artificial muscle, each electrode in an electrochemical cell acts as a fuel cell electrode, acts as a supercapacitor electrode for storing electrical energy as charge, and as an artificial muscle actually electrode for using changes in charge storage to cause dimensional changes. That, in the long term, might be the most exciting type in the muscle in the future. But at the present time, our artificial muscle that's fuel powered that gives the highest performance is very, very simple. It's not so academically interesting, but practically very interesting it is. And that is to use, just take shape memory wires, coat them with catalyst, of course with the nanoparticles. You expose this shape memory wire coated with catalyst to the proper mixture of oxidant and air, and you get a contraction as it heats up. You take away the oxidant and fuel, and it'll expand again. I'll show you a movie on that, and I'm almost finished talking, so it'll, now these fuel-powered artificial muscles can generate about 500 times the stress the force per unit area, 500 times higher force per unit area than can natural muscle. If you coil the shape memory wires into a spring, you lose some of this force capability, but you're able to get actuator strokes, which are much larger than natural muscle. In total, the overall effect is we can, each actuator stroke, we can get about 100 times the work capacity of natural muscle. Alan McDermott, who's one of my best friends in the world, who recently died, used to say science is people. Here's our artificial muscles team that for this particular work, Mikhail's from Ukraine, originally China, Korea, China, US, Philippines, US, New Zealand, Alan McDermott. Just the last few moments, I'd like to talk about a technology which I first conceived of long time ago, but which we're still working on improving at the University of Texas at Dallas with a company called Tectonic. This is a product which has long been commercial. It's a technology that's long been saving lives. And it's a chemical that is formulated as an ink, and this chemical causes is a diacylate molecule, which in the solid state and controlled by the crystal structure of in which it finds itself is polymerizing. And this polymerization results in long conjugated chains, which have about the same diameter as a carbon nanotube, have two-dimensional localization, just like for a carbon nanotube. But these color changes, dramatic color changes, we use to measure the integrated effect of time and temperature in the same way as integrated time and temperature affects product quality. So basically, we're matching activation energies for the indicator device with activation energies for perishables such as vaccine. Again, the indicator device, I have a movie which I won't be able to show you, narrated by Brad Pitt, which shows our indicators being used in the field. So basically, this is a color, outside is just a color matching region, and the inside is the diacylate. These time temperature indicators are used for all the meals ready to eat that are distributed by our Armed Force, our Army. Over 2 billion of these indicators have been so far distributed around the world. The World Health Organization and associated agency, PATH, estimates that these indicators will save over 140,000 lives over the next 10 years. So I'm very proud of this particular development. I'd like to just show you a few movies at the very end. Do we still have time? Maybe 3 minutes? Or, I always lie about time. But not much. Nothing's done in 3 minutes. I'll show you one on fuel-powered muscles. But remember, you'll see things going not too fast, but remember all we're doing is we're spraying methanol in air on these shape memory wires, and you see them contract. You'll see one that oscillates. Well, when it stops being heated because a plunger's coming up in a funnel, but then as soon as it starts cooling, the fuel and air start to again heat up the actuator. So it's not a fast on-off. It's just a question of controlling fuel. We have the carbon nanotube sheets and yarns and the fuel-powered muscles and the super tough materials have been very popular with the news media, especially TV. And I'll just show you one movie from, oh hell, I'm in the wrong file. Here's one on the super tough. That's still in the wrong file. Now remember, I'm depending upon you to laugh.
This arm wrestling robot may perform like a weakling, but it's not made with the hydraulics or gears that power most of today's big, strong machines. The robots losing this competition use artificial muscles, science's best attempt to mimic natural muscles. But University of Texas at Dallas researcher Ray
Can we turn the
Baughman
light
says
off?
we won't have the upper hand for long. He and his team have developed
Thank you.
artificial muscles that should put any He-Man to shame.
These artificial muscles are able to do over 100 times more work per cycle than a natural muscle. They're 100 times stronger than a natural muscle.
Most robotic muscles are powered by an electrical current, but Baughman's muscles are made of an elastic metal called shape memory wire, and as he reported in the journal Science, like human muscle, is powered by fuel. In this lab demonstration, the fuel is alcohol. It reacts with oxygen in the air and causes the artificial muscle to heat up and contract.
And they contract by a large amount. This contraction is like the contraction of our muscles in our body.
The muscles then expand when the alcohol is shut off. Baughman, who works with funding from the military, says these muscles could power everything from artificial limbs and hearts to super muscles for astronauts or soldiers, and maybe even self-sufficient robotic androids.
On the more humorous side, perhaps in a very distant future, the humanoid robot who is sitting next to you in a bar might be drinking alcohol in order to work the next day.
By then, challenging robots to an
Thank you.
I'm Brad Wilson.
Here again, I know the time's finished, but I just show you, this is a sheet, an example of a sheet being drawn slowly. This is a sheet being drawn slowly. And then I'll show you one being drawn at 30 meters per minute. These carbon nanotubes are sheets and yarns of are very highly commercializable technology. Here you see the Post-it note. For yarns, we prefer wooden toothpicks. But you can see the transparency. This is the logo of our institute. It'll just keep on going. It'll keep on going as long as you want to keep on drawing. So I'm not going to bore everyone. Here's the sheet being drawn fast. This is being drawn at about 30 meters per minute. Now remember, this is an aerogel, only 50% heavier than air. Look what it does next. But still stronger on a per weight basis than steel. I can show you diffraction effects or the stuff being drawn from a yarn, a forest, but I think it's better considering the time if I thank you very much for your attention.
Thank you for staying connected with Carnegie Mellon University. To learn more, go to www.cmu.edu.